Hey guys, Mrs. Trader here. We're going to do our notes on section 9.2. These are transformations of quadratic graphs. So what I want to do first is remind us of what we did in the last section, which is we looked mainly at what A tells us. And I mean A from our transformation function, our standard form, which is y equals ax squared plus bx plus c. So from this standard form, the A we mainly worked on, and we didn't have anything else over here. Like B and C were essentially 0. So when we looked at A being some number, let's compare what we know about the graph of y equals x squared and y equals ax squared. So a few different things happened. We had the case where A was greater than 1. So for example, maybe y equals 2x squared was a graph, and compared to our parent function, that was skinnier. Or maybe we said more narrow. So that made our graph go from here skinnier. Another thing that could have happened was A was in between 0 and 1. And if that was the case, for example, like y equals 1/2 x squared, our graph would have got wider. And the last thing that could have happened, and I'm running out of space, is if A was less than 0, then it went from up here to down here, and it got reflected. So A showed us a few different things. There's a lot going on with A. Now today we're gonna, on the front, look at what B does for us, how it changes our graph, and then on the back, look at what C does for us. So let's look at the first one. We've got the graph of y equals x squared plus 2x. There we go. So let's do what we've done before, and we'll graph it using a table. Usually when we were doing these, we picked points that were -2, -1, 0, 1, 2, and we centered ourselves at the origin. Let's do that now, and then later I'll show you why we would maybe pick different points than these ones. But let's do what we normally would have done for the first point. So let's see, if we plug in a -2 into our x values, we've got, and this might be scratch work for you, so I'm going to try to talk through it, but if it's a scratch work for you, then I can show you that as well. Actually, I'll show you for the first one, and then on the rest, we'll kind of go through. But what you could do is, I'm going to try to line my lines up for the most part. So let's see, if I plug in a -2, here's my thought process. Y equals -2 quantity squared plus 2 times -2. So this is -2 times -2 is 4. 2 times -2 is -4. So that's 0. My next one, if I plug in a -1, I've got -1 times -1 is 1. 2 times -1 is -2. So this is -1. My next one, if I plug in a 0, y equals 0 squared plus 2 times 0 is 0 plus 0, so 0. And then let's pause right here for a moment. We're used to seeing an axis of symmetry where everything gets reflected. And right off the bat, notice I see 0 here and here. And these were the ones that were reflected. So it reflected actually around this point, -1, -1, not at 0, 0. So if that's the reflection that's at play, then if I find this point, it would have also gone to the -3 as well. So let's check what happens at 1. If I plug in a 1, I'd have 1 squared, which is 1, plus 2 times 1. So that's 1 plus 2 is 3. And if I plugged in a 2, I would have had 2 squared, which is 4, plus 2 times 2. So 4 plus 4 is 8. So let's plot the points we have. -2, 0. -1, -1. 0, 0. 1, 3. And 2, 8. So because we know that we are symmetric, I can actually fill in another point. So this was 2 away from the origin, or 2 away from the vertex here. So let's go 2 away here. This one was 1, 2, 3 away from the vertex, so 3 away here. I can fill in some extra points to make it look nicer, and then connect everything with the curve. So let's see, it says the parent function y equals x squared is graphed for you. That's a lie right now. Let me graph it. On your sheet, it will be. So, okay, sorry. On your sheet, that's already in there. So this y equals x squared is already graphed for you. And then here is our function y equals x squared plus 2x in pink. And it says the parent function is graphed for you. What did b equals 2? So notice this one was different because we had a b term. Due to change the graph of the parent function. So it moved it, it looks like left and then down. So it moved it left / right, it could be, or up, down. So it kind of, the way I'm going to look at it is it moved where our axis of symmetry is. It was at the origin here, and now it moved left. So it moved it left, right, or up, down. Let's look at the axis of symmetry specifically. So this line that we were working with is always going to be a vertical line. And as you remember, vertical lines have equations that are x equals. So this line is at x equals -1. What this b is going to do for us is tell us how to find the axis of symmetry, which is very helpful for graphing in the future. We'll do one like that next, where we're able to use these steps and be a little bit more mindful about where we pick our points in our table. So our axis of symmetry actually has an equation. It is this: x equals -b over 2a. So this is a big one. Put a box or a square or a star by it or something like that, maybe a smiley face. So we've got x equals -b over 2a. If you know what your a is and you know what your b is, then you can find your axis of symmetry, which is where you reflect around. So here's going to be the steps moving forward, since we know this now, in order to graph. First, what we'll do is we'll find our axis of symmetry, that's AOS, using the equation that's above. Then we will place the x value in the center of the xy table. So let me pause there. Let's do step 1 and 2 on number 1. So let's see. We've got our A is 2, and our B is 8. So my axis of symmetry, remember, is -b over 2a. So -8 over 2a. -8 divided by 4. -8 divided by 4 is -2. So our axis of symmetry is at x equals -2. So I can plot that right now. And okay, so that's where we're at. We've done number 1. Find or place the x value in the center of the xy table. So we said x equals -2. That's going to go in the center of our xy table, the middle spot. And then number 3, fill in x's to the left and right of the axis of symmetry. Fill in x's. So here's our x's. To the left of -2 is -3 and -4. And to the right of -2 is -1 and 0. Now, lastly, it says evaluate y's and fill in their symmetrical pairs. So it looks like we have 5 things to solve for, but actually, because of the fact that these are going to be paired here and these are going to be paired here, we don't have to find as many. We kind of get 2 for the price of 1. So once I fill out one of them, I have the other as well. So let's find our vertex first. I like to start there. If we plug in a -2 to our equation, I've got maybe some scratch work. Maybe you're good at doing this in your head. This part is kind of on you. But you are plugging in a -2 to this equation. So we'd have y equals 2 times -2 quantity squared plus 8 times -2. So let's see. -2 times -2 is 4. 8 times negative 2 is negative 16. So we've got 8 minus 16 is negative 8. So we've got a vertex at negative 2, negative 8. Of course I went off the graph. Of course I did. Negative 2, negative 8. And then let's check out the rest of the guys. I like to plug in smaller numbers rather than bigger numbers. So I'm going to choose this one with a negative 1. So if I plug in a negative 1, I'd have y equals 2 times the quantity negative 1 squared plus 8 times negative 1. Negative 1 times negative 1 is 1, so this is just 2. 8 times negative 1 is negative 8, so that's negative 6. And if this guy is negative 6, so is that guy. Next, let's plug in a 0. Y equals 2 times 0 squared plus 8 times 0. 0 squared is 0, so this whole thing's 0. 8 times 0 is 0. So this guy is a 0. And then, therefore, so is this one, because they're symmetric. All right, so we've got our 5 points. So let's go ahead and plot them. We already have our vertex plotted. Let's go to negative 4, 0. Negative 3, negative 6. Negative 1, negative 6. And 0, 0. So it made it easier since we had our axis of symmetry to go around. Here is our graph then. And I'd prefer if you continue on these lines all the way to the edge. Throw some arrows on them to indicate that they keep going. Let's try another one like that. This next one, we have y equals 3x squared plus 6x. So first off, let's notate what our a and our b are. A is 3, b is 6. So our axis of symmetry is, again, negative b over 2a. So we've got negative 6 over 2 times 3. So negative 6 over 6 is just negative 1. So we've got this axis of symmetry at negative 1. I'm going to put a dashed line in there so we know where axis is. And then we can put this axis of symmetry as the center point because that's going to be part of our vertex. Let's find the y-coordinate of our vertex next. So let's see. If we plug a negative 1 in here, I'd have negative 1 times negative 1 is 1. 1 times 3 is 3. 3 plus 6 times negative 1 is 3 minus 6. That's negative 3. So I've got my vertex, negative 1, negative 3. That vertex will always be on the axis of symmetry. Now let's find some points to the left and the right. So to the left, I've got to the left, I've got negative 2 and negative 3. And to the right, I have 0 and 1. Because of the fact that these are going to mirror, you know that you only have to find 2 more points. And if I were you, I'd pick the easier ones to find, which are generally the positives. So let's plug in our 0. If that's the case, since there's x's in both terms, they're going to cancel out and become 0. So if that guy's 0, symmetrically, so is that one. If I plug in a 1, I've got 3 times 1 times 1, that's 3, plus 6 times 1, so 3 plus 6 is 9. So there we go. We've got everything we need. Negative 3, 9. Negative 2, 0. 0, 0. And 1, 9. So let's plot this guy, give it a curve. Oh, that was bad. There we go. There is our equation. So again, one thing to notice as well, if I take a step back and look at both of these, remember back to our a values. This one had a equals 2, so it was skinny. This one had a equals 3, so it was even skinnier yet. So that's another thing to notice. And then again, our axis of symmetry moved based on our b. So we've talked A, we've talked B, we have not yet talked C, so let's do that. Let's look at this equation, y equals x squared plus 4. So let's think about our A's, B's, and C's. Remember, our standard form looks like this. So we have an A value because it's in front of the x squared. Our A value is 1. Our b value goes with the x term, which we don't have a regular x term, so that's 0. Our c value we do have in this case, that's c equals 4. All right, I threw in that parent function that we'll need. So let's see. It says the parent function y equals x squared is graph for you. Well, now it is. What did c equals 4 do to change the graph from y equals x squared to y equals x squared plus 4? So let's see what happens here. We can still find our axis of symmetry because we have a and b. So axis of symmetry, negative b over 2a. So negative 0 over 2 times 1, which is just 0. So I've got a vertex at 0 something. Let's figure out the something that goes with it. If I plug in a 0, I'd have 0 squared plus 4 is 0, 4. So there's my vertex at 0, 4. And then let's find the rest of our points. We'll go to the left, and to the right, to the right. And because we know that symmetry is going to happen around the vertex, I can just find my positive 1 and 2 points, and then I can copy them over with symmetry. So let's plug in 1. I'd have 1 squared is 1, plus 4 is 5. So then a 5 also will go there. If I plug in 2, I've got 2 squared is 4, plus 4 is 8. So I've got an 8 there, and then with symmetry up there as well. Let's plot these extra points. Negative 2, 8. Negative 1, 5. 1, 5, and 2, 8. So connect your points. And it looks like what happened here, you can't really tell. This guy is black and this guy is purple, but we moved up 4. So what did this do to the parent function? It moved us up 4. And we could reason that if c is greater than 0, then it would go up. And if c was less than 0, it would go down. So you can imagine if this was minus 4, then it would have just dropped the whole thing down. So those are a couple things happening with c. Let's graph 2 more, and then we'll be pretty close to calling it a day here on these notes. So on number 5 and 6, there's a's, b's, and c's. We'll follow the same steps that we did on the front. So number 1, let's find our axis of symmetry. We've got negative b, so negative 6 over 2 times a. So 6 over 2 is 3. So we've got an axis of symmetry at 3. That means our vertex has an x-coordinate of 3, and I can put that at the center of my table. Let's plug a 3 in now. So I've got 3 squared is 9. Minus 6 times 9, we might need some scrap paper here. I'm going to keep pulling in Post-it notes along the way. So for our 3, we've got, actually, I'm going to move it down here. There we go. For our 3, we've got 3 squared minus 6 times 3 plus 4. Okay, so we've got 9 minus 18 plus 4. 9 minus 18 is negative 9 plus 4 is negative 5. So there's my vertex at 3, negative 5. Let's look at my next one here. Let's go to the right of 3 at 4 and at 5. And then we'll go to the left at 2 and at 1. So at 4, we would have 4 squared minus 6 times 4 plus 4. So we've got 16 minus 24 plus 4. 16 minus 24 is negative 8. Plus 4 is negative 4. So I've got negative 4 here, and then symmetrically I also have it up here at the 2. My last one is at 5. So I've got y equals 5 squared minus 6 times 5 plus 4. So I've got 25 minus 30 plus 4. Negative 5 plus 4, that's at negative 1. So I can plug in a negative 1 at those spots. All right, so I've got all my points. Let's plug them in. I've got a point at 1 at negative 1. one at 2, -4, one at 3, -5, that's our vertex, one at 4, -4, and one at 5, -1. This will keep going on and on forever. It just went off the graph, so will that one. Let's look at one more. And let's see. Actually, what I'm going to have you do here is try this one out. Take a moment and pause your screen, and then you can put play, and then I'll have the answer for you. So you try 6, start to finish, find your axis of symmetry, set it up in the center of your table, and then graph your parabola wherever it is. Like I said, I'll pause my screen. When you hit play, you can go ahead and check it. So go ahead and pause now. All right, here's what I have for the graph. We've got our vertex is at -1, -1 down here. These points kind of went off my graph, but you get an idea where they're heading up to. Hopefully this one looks okay. Let's look at one more. And there's not a graph to be written in this one. We just want to think about a situation. So it says the height of a baseball hit by a 6-foot tall Tigers player is modeled by the equation below, with H representing the height of the ball in feet and T representing the time in seconds after the ball was hit. How high will the ball go at its maximum height? So let's first think reasonably. If we were to hit a baseball, it would be going like this. And we want to know how high would the ball go. So basically what it's asking for, when it says how high will the ball go, it wants to know the vertex. And these vertexes, notice it's H's and T's, not X's and Y's. Usually the vertex is X, Y, but we have vertexes that are TH, and H represents the height. So really what they want is the Y coordinate of our vertex. And we can get our vertex with the axis of symmetry. So let's first find the X coordinate, the T coordinate, I should say, of the vertex. Then we'll plug that in to get H. So we've got our axis of symmetry is going to be -b over 2a. So -55 over 2 times -16. So let's plug that into a calculator and see. We've got -55 divided by -2 times 16. So we have about 1.7 here. So approximately 1.7. So right now we have this piece, and we need the next piece. That'll be our answer. So let's plug in 1.7 to our original equation. So we've got -16, 1.7 squared, plus 55 times 1.7, plus 6. So I typed it all in my calculator. It's going to tell us we're at 53.26. So at 1.7 seconds after he hits the ball will be at a maximum height of 53.26, and we're talking about feet. So 53.26 feet is the height of the ball. And reasonably, that makes sense. The height of a basketball hoop is 10 feet up. So 5 basketball hoops in the air is how high this went. And that's pretty realistic to a baseball hit. This is probably a pop fly to center. Later, we will look at different types of questions that modeled by baseball really well, where we look at maybe where did it land or how long did it take to land. Those are other questions we'll be able to answer eventually. So hopefully this helped. I will see you guys next time.